So, now that we have studied a 2-channel filter bank, we can generalize this in a natural way to an arbitrary M-channel filter bank. So, the idea is very simple. Instead of 2 filters, we have M such filters stacked, and they form the analysis bank if they are analysis filters, and these analysis filters will be followed by downsampling by M. If you have M channel filter banks, then you will have upsampling by M to restore the sampling rate, and then your synthesis filters that you combine all these subband signals, and then you get the reconstructed signal at the output. So, now this is the idea. So, let us sketch the schematic first. So, we have x of n, we have h naught of z, this interim point is x naught of n. I have downsample by m. Let us say the signal here is v naught of n, and remember at this stage you can do whatever you want for quantization, compression, etc. But if you did not do any quantization and compression, we will just feed this signal to an upsampler by m. The interim signal is u naught of n post the upsampler, followed by filtering through the synthesis filter f naught of z. So, this is one branch. So, you can imagine m such branches. So, we do this similarly. We have h1 of z, you have a downsampler, you have an upsampler, filtered through f1, we have h m minus 1 of z, a downsampler, an upsampler, a synthesis filter f m minus 1 of z. I combine all the outputs and I get x hat of n, which is a reconstructed signal. So, this is the analysis bank of filters. These are the downsamplers, these are the upsamplers, and these are our synthesis filters, and this is collection of synthesis filters forms the synthesis bank, and this forms the analysis bank. Okay. Now, I think with this picture in mind, and you can think about interim signal, if this is x naught, this should be x1 here, this should be v1, u1, correspondingly so on. So, I think you can get the picture what is really happening here. So, let us define some notations that we will use towards the analysis. Let h of z be a column vector comprising of the analysis bank. This is H naught of Z, H1 of Z, dot 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 H m minus 1 of C. So this is a column vector. Similarly, we have F of Z is a stack of the transposed synthesis filters. And you may wonder again why we want to make a distinction of this transposition here. This is again type 1 and type 2 representation within the polyphase decomposition that would play a pivotal role in the way we would look at the structure for the analysis and the synthesis bank of filters. So, let E of Z be a delay chain which is required for polyphase, and that is a unit delay dot 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 a delay of m minus 1 units. This is delay chain. Needed for polyphase representation. Okay. Now, with this we are sort of set. So, all we have to look at is the Z transform of the interim variables x naught of n, x1 and so on and so forth, and then express it in a compact form towards the analysis of what the overall transfer function is and how we can cancel the alias, and if you want to remove the alias, what we need to do. So, we start with the usual analysis that we are comfortable. Xk of Z is Hk of Z times x of Z, and of course this is k equals 0, 1 dot 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 till m minus 1, right. If you recall, for a 2-channel filter bank we had just k equals 0 and 1, just 2 components. Here we have m components 0 to m minus 1. So, therefore, xk of Z is this for k equals 0 to m minus 1. Then we have Vk of Z, which is the output after the downsampler, right, and we know the equation for the output of the downsampler. And I have conveniently ignored the subscript m here in omega, and this is basically e power minus j 2 pi upon m. Then we have Uk, which is Vk of Z power m post expansion, and you can write this as 1 upon m sum L equals 0 to m minus 1 x of Z omega power L H k of Z omega power m. So, this step is also straightforward. Now, we can get the relationship, the expression for x hat of Z, which is basically you are taking all the subband signal post the upsampling process and filtering them through the bank of synthesis filters. So, this is summation k equals 0 to m minus 1 fk of z uk of z, and if you simplify this you get 1 upon m summa L equals 0 to m minus 1. So, we will put the uk here, plug this in, x of z omega power L and summation k equals 0 to m minus 1 hk of z omega power L with fk of z. Right, the k equals 0 is what we want to bring in, and this u we just express it out using this equation, right, and this x does not have any k dependency. So, you pull this out and you can simplify this in this form. Okay. Now, we can rewrite this messy equation slightly in a form that is presentable. Rewriting in an easier way, x hat of z is summa L equals 0 to m minus 1 a L of z times x z omega power L, where a L of z equals 1 upon m summa k equals 0 to m minus 1 hk of z omega power L fk of z for all the m components. Okay. Now, with z equals e power j omega, x of e power j omega times, we take this omega power L, and that is for all L from 0 to m minus 1. This is basically a shifted version of the spectrum, which is basically translated version of the base spectrum at points 2 pi L upon m. Okay. So, L equals 0, 1, 2, 3, so on till m minus 1, you plug this thing here and you get the translations of the spectrum that are uniformly shifted. Now, these components x of z omega power L for L equals 1 to m minus 1 are alias components. Right, x of z is what we want, and the rest x of z omega power L for L from 1 to m minus 1 are alias components. It is exactly like what we had for the 2-channel bank, where when L equals 1 with m equals 2, we had the minus 1 that was appearing before z, right, and that was our alias component. This is just a generalized version. Of course, a little bit of detail before we wrap up with the slide. Do not just confuse with the omega that is here, which is a frequency, and this w, which is basically the mth root of unity, right, and this is a small detail. So, I think you can now to avoid aliasing, AL of Z has to be 0 for all these components, L equals 1 to m minus 1. Okay. So, let A of Z be a stack of all polynomials in Z, starting with the unaliased component with the rest of the aliased components. Let H of Z, this is really bold matrix, be a stack of matrices given as follows: H naught of Z, H1 of Z dot 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 H m minus 1 of Z, then you have H naught of Z omega, H1 of Z omega dot dot H m minus 1 of Z omega. So, you have H naught Z omega power m minus 1 Z omega power m minus 1. So, this is our m by m alias component matrix or our AC matrix. So, we had the AC matrix for a 2-channel filter bank, which we had just 2 components, right. It was a 2 by 2 matrix. Now, generalizing this, we have an m by m matrix, which is the alias component matrix. Now, if you look into this carefully, I mean, if you want to avoid aliasing, you have to set all the AIs I equals 1 to m minus 1 to 0, right. So, that is what you want to force, and therefore, your overall distortion function would be just A naught, which would be your unaliased version. Okay. So, we will go one step further. With aliasing cancelled out, the distortion function T of Z is 1 upon m summa k equals 0 to m minus 1 hk of Z fk of Z, and we call this as A naught Z. Okay. Now, m times this A of Z, which is A naught Z through A m minus 1 of Z, is essentially this alias component matrix H of Z times f of Z, right. You are just rewriting this in a matrix form, and we call this sum T of Z. But AL of Z is 0 because we want to remove the alias components for 1 less than or equal to L less than or equal to m minus 1. So, since this has to be forced, to 0, our T of z is essentially of the form m times a naught of z, the rest being zeros, and this is m times T of z, which is your overall distortion function with aliasing cancelled out, and the rest all being zeros. Okay. Now, with this in place, we can write down the expression for x hat of z for your reconstructed signal. X hat of z is basically A transpose z times x of z so which is basically 1 upon m f transpose of z h transpose of z x of z. Where x of z is our usual vector which has the unaliased component of the signal with all the aliased versions. Now, f of z is H inverse T of z, because we said H of z with f of z is T of z, which is our transfer function, right. If you start here, H f is T is what we start with. So, therefore, the synthesis filters can be obtained with the knowledge of the overall transfer function T of z that we want with the alias component matrix. Okay. Now, this is realizable. So, at one shot we are getting all the synthesis filters. This is in vector form f naught, f1, f2, so on till fm minus 1, we get all the synthesis filters at one shot. So, that is the reason why we have adopted the matrix form of representation. You may question, now I want to get f of z, that means H has to be invertible, right. It is realizable if H inverse exists, right, otherwise we have difficulties. Now, for perfect reconstruction, we force T of z to take this form z power minus n naught, rest all being zeros. If you want, you can put a scalar here, it's okay if you want to bring in some scalar c, but we want it to basically be a delay with some gain and the rest of the components are all zeros. Now, you may wonder at the moment what are the difficulties with the AC inversion matrix, right. We said the synthesis filters can be realized by inverting the alias component matrix, and that is a critical step, and there would be difficulties if we cannot invert invert this. So, we will study some of the issues related to the inversion. Unless the magnitude of h of z is not equal to 0 for every z, we are in trouble. Towards getting h inverse of z. Right? I mean, because if you think of realizing h of z as magnitude of h of z times some e power j phase, and if you have to invert it, you are having a 1 over the magnitude of h of z in the denominator, right, and that should not be 0. Second, we have f of z, that is the synthesis filters, can be realized as 1 over determinant of h of z adjoint of h of z times t of z. Now, you see the difficulty here. If the analysis filters are FIR, synthesis filters can become IIR, because we have a denominator polynomial that can occur because of the determinant. Can give rise to a denominator polynomial which may not be just a delay. With a gain. Okay. So, if you had a delay and a gain, then there is no issue, but you may not guarantee the determinant to be just a delay with a gain. So, therefore, even if analysis filters are FIR, synthesis filters can be IIR, right, and now we know the trouble with IIR filters. Round off noise, stability, and lot of these issues are there, right, and when you do quantization, even a small shift in the pole position, right, can alter your response significantly, or you can drive the system to instability, right. These are very, very important considerations. So, I think as an offshoot of this, I mentioned to you that this implies that stability can be a problem. Then there is one other issue. If determinant of h of z has zeros on the unit circle, that is z equals some e j omega naught, then magnitude of t of e j omega naught is 0, right. If it has a 0 on the unit circle, then magnitude of this t e j omega naught, that becomes 0, which means severe amplitude distortion around omega naught. Now, T of z, capital T of z is the transfer function that we saw, right, that is for the unaliased part, right. If you look at the unaliased part, that is the transfer function. So, I think just to recall, this is for unaliased part, this is function. Okay. So, that is an issue. If the magnitude of t of e j omega naught equals 0 at those positions omega naught, right, those frequencies, this implies that you would have severe amplitude distortion around that frequency. So, then you can imagine what should be the order of the filters, etc., and perhaps the issues that you will have to deal with when noise gets amplified around those frequencies, etc. So, these are some practical issues that you will have to deal with. So, with this, let us carefully look into the singularity issues. In h of e j omega and linking it to the amplitude distortion. So, we saw that if t of z has a 0 at z equals e power j omega naught, then t of e j omega naught equals 0, but this t is related to h and f, because we can say that this is h of e j omega naught times f of e j omega naught, and that is t of e j omega naught, and that is essentially 0, which means h of e j omega naught is singular unless all synthesis filters fk of z have a 0 at omega naught. Right, and t of e j omega naught equals 0 in an alias free system, and this implies that there is singularity of the AC matrix at omega equals omega naught. So, this is what really happens. So, if you want the t of e j omega naught to be equal to 0, right, then this would imply that this expression h of e j omega naught with f of e j omega naught is equal to 0, and we know that f is basically a transpose stack of all the synthesis filters, and this is singular unless all synthesis filters have a 0 at this frequency, right, and this is the implication of amplitude distortion, which links the singularity in the alias component matrix. Okay. So, with this we are sort of set, we have derived an equation, an expression for the reconstructed signal for an M-channel filter bank. So, we have analyzed how the distortion function looks, and the matrix formulation has been very convenient for us, right, by looking at the alias component matrix, then all the components in the signal, the unaliased components and the alias components and the synthesis filters, we can link all the quantities together towards an overall distortion function, and if you force the alias conditions to be 0, then you land up with the unaliased distortion function, and then we see what is the relationship if you know we have to get realizable synthesis filters, and what are the issues when we have to consider difficulties with the AC inversion matrix. Okay. So, these are all important considerations. So, hopefully with these set of tools we are set for analyzing an M-channel filter bank. So, the idea is again very simple, we start with a base filter which is the mother filter H naught of Z, and then we can realize all the synthesis filters, I mean for AC cancellation, as well as the analysis filters via translation of the base filter. Okay. So, with this we complete this part, and then we are ready to start with the polyphase representation of the M-channel filter bank.